Adam's going to draw for us right now all of the forces that act on car number 1 during the collision with car number 2. So they're going towards each other, they're going to hit each other, they're going to collide, they're going to come to a crashing halt. Adam's going to draw all of the forces acting on object number 1 or car number 1. Just on one. Yeah, just on one. Okay, what's he got labeled right there? You guys can help him out there. Okay, hold on for a sec. Adam, back up for a sec. First one was the force of gravity, yeah. So label that FG. Second one that he's drawn is the normal force, yeah. So we're going to call that Fn. He's got them drawn the same length. Should they be drawn the same length? Yeah, absolutely. Absolutely. So far, so good, Adam. Okay, now he's going to draw force 1. Okay, and is that it? Okay, so now he's going to draw force of air. You know what? Let's say there's no air resistance. Okay, it's just the cars colliding, no friction, no air resistance, nothing like that. We don't want to complicate it more than we have to. It's already a little bit tricky, actually. So we're not going to make it any more complicated than we have to. Okay, okay, so draw that, F2. You guys agree with that? Okay, I'm going to tidy this up a little bit. Looks good, Adam. Looks good. I'm going to tidy this up a little bit. Okay, I'm going to get rid of this car, okay? Just so the thing's not cluttered, right? Okay, so now we've got Fg acting down, same value, Fn as Fn acting up. Agree? They cancel each other out, right? Because they're equal and opposite forces. We've got F2 pushing to the left, F1 pushing to the right. For every action, there's an equal and opposite reaction. He's got them drawn the same length, correct? Is that good? So they cancel out too, right? What's the net force acting on that car right now? What's the unbalanced force acting on that car right now? What is it? 0. If Newton's third law, as we've stated it, and as your grade 7 science teacher stated it, for every action there's an equal and opposite reaction, truly applies, then won't it always be the case that there's no net force acting on an object? If there is no net force acting on an object, how can the object stop? This car is moving. Thank you, Adam. This car is moving. If this car is moving and it has no unbalanced force acting on it, won't it always keep moving in a straight line at a constant speed? If it was at rest, wouldn't it always stay at rest until acted upon by an unbalanced force? You can't have an unbalanced force because there's always an equal and opposite reaction force that balances it, right? This is why I don't like the way that Newton's third law is typically stated. For every action, there's an equal and opposite reaction. Because it leads us to this apparent conflict, which isn't really a conflict at all. It just seems like it is. There's a fundamental flaw in the way this is drawn, and the reason I had a volunteer do this is because I knew that's how you were going to draw it. Everybody always draws it like that. I would have drawn it like that when I was in grade 11. I didn't understand it any more than you guys do when I was in grade 11. There's a good chance your science teacher didn't completely understand Newton's third law. It sounds like the easiest law. For every action, there's an equal and opposite reaction. I would argue it's probably the hardest of the 3 laws. Even harder than the first one, which sounds kind of confusing. I think this one's harder. I want to restate Newton's third law. Let's put this car back, first of all. Car number 2. There we go. Car number 2 is back now. I want to restate Newton's third law. I'm going to state it as in the following way. If instead of for every action there's an equal and opposite reaction, I want to state it as if object A applies a force on object B, then object B will apply an equal and opposite force on object A. That's not much different than the way that you've always heard Newton's third law. But I think it clears up the misconception that Adam drew on the board and that all of the rest of you are probably thinking. If object A applies a force on object B applies an equal and opposite force on object A. I'll put it back to that slide in a second for you to finish writing that. Let's erase these 2 forces, 1 and 2, for a second. If object 1 applies a force on object 2, then object 2 will apply an equal and opposite force on object 1. Now let's take away that car, that second car. And the force that acts on it as well. Now look what I've got. Now I've got a car that just collided with another car that has a net force acting on it. There were two forces. There was an action force on car number 2. There was a reaction force on car number 1. It's important to know that those two forces are acting on different objects. That's what allows us to have a net force. That's what allows this car to stop, because it's got a force opposite to the direction that it's moving. We hear for every action there's an equal and opposite reaction. We all think the same thing. Oh, look, there's a force to the left. There's got to be a balancing force to the right. There is a force to the right. But because that force to the right is on the other object, it doesn't balance it at all. The two forces to balance, they have to be acting on the same object. Does that make some sense? If object A applies a force on object B, then object B applies an equal and opposite force on object A. This way of stating Newton's third law reminds us that we're dealing with two separate objects, not just one object. Let's give some examples of some action-reaction forces. Again, to identify, to recognize that we're acting on two separate objects here. Kick a soccer ball. Okay, kick a soccer ball. Wait, who's a soccer player? Okay, kick a soccer ball. When you're a little kid, probably 3 or 4 years old, you probably kicked a soccer ball with your toes. Sometimes maybe you hurt your toes. Ever do that? Maybe you still do that sometimes by accident and hurt your toes, right? Not on purpose, but what's the action force? What's the action force involved in kicking the soccer ball? The force of your toe, in that case, on the soccer ball, right? What's the reaction force? If I apply a force on the soccer ball, then the soccer ball applies, an equal and opposite force on your foot. Let's go to Wally again, back to Wally videos that I showed you. If the fire extinguisher applies a force on the powder that's inside the fire extinguisher and propels it forward, then the powder applies an equal and opposite force on the fire extinguisher. That means when you push it forward, it pushes you back. That's why Wally went backwards when he expelled the gas out of the fire extinguisher. How about an airplane? When you apply a force on the air behind the air applies a force back on you? No. When the engine of the airplane applies a force on the exhaust from the airplane, then the exhaust from the airplane applies an equal and opposite force back on the airplane. Has nothing to do with the air, because then propellant wouldn't work in space, right? When you're propelling a spacecraft. When you apply a force on the exhaust, whatever it is, it's not combustion in space, but whatever the exhaust is, then it's going to apply an equal and opposite force back on you, a thrust force back on you. Ever done this? At some point you have, everybody has. You get up in the middle of the night to go to the bathroom. You kick the end of the bed, and it hurts your toe, right? Why does it hurt your toe? Does it hurt your toe because you kicked the bed? No. It hurts your toe because the bed kicked you back. Yeah. Don't do this, okay? Don't ever do this. Now, let's say you got in a fight at school, okay, which none of you guys are ever going to do because you're all good, right? Let's say you get in a fight at school and you punch somebody in the face. And you get hauled into Mrs. Staffichuk's office, and Mrs. Staffichuk says, "What were you thinking punching that person in the face?" And you say, "Well, it's not just me. Like, he did it too." She says, "What do you mean? He's got a bloody face." And you say, "Well, when my hand punched him in the face, but his face punched my hand back just as hard. with an equal and opposite force. Yeah, but you did it first. No, you can quite truthfully say, I punched him in the face, but his face punched me back in the hand at exactly the same time.
What would you say then?
I don't know. I wouldn't want to try it. Yep, question? All right. All right, have a look at this. What are we doing there? We're punching glass. Hey, you know what? Let's make it a little bit less painful to the hand. Let's throw a rock at the glass, or let's throw a brick at the glass. Hey, there's a piece of glass over there. Let's pretend we're throwing a brick at it. When I throw a brick at that glass, what's going to happen? Well, there's a good chance the glass actually won't break. It's laminated glass, and there's a good chance that that glass will not shatter when it's hit by a brick. It's designed to be that way. Okay, some glass will, some glass won't break, not very easily when it's hit by a brick. A windshield. Okay, a windshield is designed to take a huge impact. It's laminated glass. It's got this thin layer that prevents it from shattering into a million pieces when it's hit by something. Because you get hit by things all the time at 110 or 120 kilometers per hour. There's a good chance it wouldn't break. If I throw the brick at that glass and it doesn't break, does Newton's third law apply? In other words, when the brick applies a force on the window, does the window apply an equal and opposite force on the brick? Yes or no? Yes. Yes, it does. Absolutely. Okay, the brick applied a force on the window. Well, the brick would have kept going if the window didn't apply a force back on the brick. Okay, let's take it to the next step, though. Let's throw the brick at the window. Let's say the window does break, and the brick goes right through the window and hits the wall over there on the other side of the hallway. Did the brick apply a force on the window? Yes, the window broke. The window doesn't break unless there's a big force applied on the window, right? But does Newton's third law hold in this case? Did the window apply an equal and opposite force on the brick? Guy's saying yes. You said yes? Okay, I thought you were just nodding your head. Yeah. Yeah. Anybody else agree with them? Yes? How does the window apply an equal and opposite force on the brick if the brick goes right through the window? Slows it down. All right. Well, why doesn't it stop it? Why doesn't it stop it then? Yeah. Okay, so if it breaks, if it doesn't break, it's an equal and opposite force. But if it does break, maybe it's a lesser force. That makes sense, right? Still a force because it slows it down, but not a big enough force to stop it. Well, we're partly right there, but not completely. The window does apply a force backwards that would slow it down. And it's not a force that's big enough to stop the brick. But it is an equal and opposite force. If the brick applied a force on the window, even if it breaks, while it's still in contact with the brick, will apply an equal and opposite force back on the brick. So why did it keep going, and why did the window break? Well, whatever force that the brick applied on the window was a strong enough force to break the window. That same force that was applied back on the brick was a strong enough force to slow down the brick, but it wasn't a strong enough force to stop the brick. So it can be an equal and opposite force. Of course it is. You're going to get a question on a test coming up. It says, a mosquito hits a semi-truck, goes squish. How do the forces compare? Well, a mosquito is object A. It applies a force on the semi-truck object B. The semi-truck applies an equal and opposite force back on the mosquito. How's that possible? The mosquito goes squish. The semi-truck doesn't even notice. Well, the force that the mosquito applied on the semi-truck was so little that the semi-truck doesn't notice. The equal and opposite reaction force on the mosquito was just as small. It just doesn't require very much force to squish a mosquito, that's all. You need a lot more force acting on a semi-truck to do anything to it than you do on a mosquito to squish the mosquito. Yep.
So, for example, a large truck hits a tree.
Yeah. So, for example, hypothetically, now, Nick, Aurora's truck hits a tree.
The tree hits back.
If the tree hits back, yes. So I don't know. How your insurance is going to deal with this if you go through insurance, Aurora. But if you do, now, and they try to tell you like your insurance rates are going to rise because you hit a tree. Your response to that can be,
No, the tree.
well, I did, but it was just as much the tree's fault as mine. They say, how so? You say, well, the tree hit me back at exactly the same time as I hit the tree. And it wasn't me that did the damage to my car. It was the tree that did the damage to my car.
And I know the exact tree.
There you go. Did the tree break? Did the tree break when you guys hit the tree? No. But the truck dented. So what's happening there is object A applied a force on B. The car applied a force on the tree. The tree applied an equal and opposite force back on the car. So that force was enough to dent a car, but that exact same force wasn't enough to break a tree. Okay, same force, just it's enough to do something, but not enough to do something else. Does that make sense, guys? Yeah? All right, we're going to wrap it up there for today.